Welcome. Today, we're diving into one of the most fundamental materials in civil engineering, the brick. We're going to break down the core principles of how we evaluate them, a skill that is absolutely essential for any engineer.
You know, when you think about it, almost every structure, from a simple home to a massive civic building, often starts with this single, humble unit. It truly is the building block of our modern world.
And this is the crucial point. Some bricks are strong enough to stand for centuries, while others can degrade and fail in just a few years. The difference comes down to how they're made and what they're made of.
And for us as engineers, knowing that difference isn't just academic, it's a professional obligation. Being able to properly evaluate and select the right brick directly impacts the safety and durability of everything we build.
So here's how we're going to tackle this. First, we'll cover the fundamentals of classification. Then we'll look at how to measure a brick's quality, both on-site and in the lab. We'll get into the 3 most critical tests that give us the hard data we need. After that, we'll see how we use that data to match the right brick to the right job. And finally, we'll wrap up by talking about our responsibility as engineers.
All right, let's start at the beginning. Before we can even think about testing a brick, we need a system to classify it. This gives us a solid framework for everything that follows.
The most basic way to classify bricks is by how they're made. On one hand, you have sun-dried bricks. They're exactly what they sound like. Clay mixed with water, formed, and just left out to dry. As you'd expect, their strength is quite low, so they're only good for very temporary structures. On the other hand, you have burnt clay bricks. These are fired in a kiln at very high temperatures. We're talking 900 to 1100 degrees Celsius. This process fuses the clay particles, giving the brick much higher compressive strength. These are the bricks we rely on for our permanent structural walls.
Now, within those burnt bricks, we have 4 distinct classes to standardize quality. First-class bricks are the best of the best. High strength, low water absorption, perfect for exposed, load-bearing walls. Second-class bricks are still good, but they're typically used for walls that are going to be plastered over. Third class have lower strength and are really only for temporary work. And then you have fourth class. These are overburnt, brittle bricks, often called jama, that we can't use for building, but they're perfect for crushing down and using as aggregate in road foundations.
Okay, so now we know the classifications. The next logical step is to figure out how we actually measure that quality. How do we confirm if a brick is first class or third class? This involves both quick checks on a construction site and precise measurements in a lab. So, imagine you're on site and a truckload of bricks arrives. What do? You perform a few quick field tests. First, a visual inspection. Are they uniform in shape? Do they have sharp, clean edges? Any visible cracks? Next, a soundness test. You take 2 bricks and strike them together. You want to hear a clear metallic ringing sound. A dull thud is a bad sign. It means they weren't fired properly. And finally, a simple hardness test. You try to scratch the surface with your fingernail. If it leaves a mark, the brick is too soft. These simple checks give you a really good first impression of the batch's quality.
But look, those field tests are great for a quick check, but they're subjective. For any serious structural work, we need hard, quantitative data. That's when we turn to standardized laboratory tests, like those outlined in IS 3495. The first, and without a doubt the most important property we test for, is compressive strength. Simply put, this is the brick's ability to resist being crushed. For any wall that has to support weight from above, which is most walls, this is the single most critical characteristic. And here is the number you need to remember. For a brick to be considered first class, its compressive strength must be greater than 10 megapascals. That's the baseline. This is a non-negotiable threshold for structural work.
So, how do we get that number? The test is quite straightforward. We take at least 3 sample bricks and place each one in a machine called a compression testing machine, or CTM. The machine applies a slow, steady load until the brick cracks and fails. We record the maximum load it could take, divide that by the brick's surface area, and that gives us its compressive strength.
The second critical test is for water absorption. This tells us how porous the brick is, how many tiny holes and voids it has inside. Why does this matter? Well, a porous brick is like a sponge. It soaks up water, which can lead to frost damage, salt attack, and a general breakdown of the brick over time. It's a direct indicator of long-term durability. And here's our second key number. For a first-class brick, the water absorption must be less than 20% of its dry weight. Anything higher than that, and you start to seriously worry about its ability to withstand weathering over the decades.
The test for this is also very simple. You start by weighing a completely dry brick, we'll call that W1. Then, you submerge it in water for a full 24 hours. You take it out, wipe the surface dry, and weigh it again. That's your saturated weight, W2. The formula is then just the change in weight divided by the original dry weight times 100. That gives you the percentage.
Finally, we test for efflorescence. You've probably seen this before. It's that white, powdery stain that appears on some brick walls. This isn't just a cosmetic issue, it's a red flag. It tells you there are soluble salts inside the brick. When water gets in and then evaporates, it draws those salts to the surface, and this process can literally cause the brick to crumble and decay over time. It's a major problem, especially in damp or coastal areas.
Okay, so we've run our tests, we have our data on strength, absorption, and salts. Now comes the real engineering work, putting it all together to choose the right brick for a specific job.
This decision matrix really sums it up. For a critical, load-bearing wall, you don't compromise. You use a first-class brick because you need that high compressive strength. But for an internal partition wall that isn't holding anything up, a lightweight hollow brick is a much smarter choice because it reduces the total weight, the dead load of the structure. For a pavement, you need something tough that resists wear, so a concrete brick is a great option. For an industrial furnace, you need a specialized fire brick, a refractory brick that can handle insane temperatures. And if you're building near the coast, the #1 priority is resisting salt and water, so you must choose a brick with very low absorption to prevent efflorescence and decay.
So to wrap things up, let's take a quick look at where materials are heading and bring it all back to the core principles of what it means to be an engineer.
You know, the industry is constantly evolving. We're seeing a big shift towards sustainable materials like fly ash bricks. These are great because they use an industrial waste product, fly ash, instead of valuable topsoil. They often have a smaller carbon footprint, and they can be manufactured to be more precise and offer better insulation than traditional clay bricks.
But no matter what material we use, this is the bottom line. Choosing the right brick isn't a small detail. If you get it wrong, you impact the building's durability, its long-term cost, and most importantly, you affect the safety of the people who will use it.
And that's why this entire process, the classification, the field checks, the lab tests, the final selection, it's not optional for us. It isn't just best practice, it is a fundamental core responsibility of our profession.
So I'll leave you with this thought. The next time you walk past a brick building, I want you to look at it differently. Don't just see a wall. See a series of critical engineering decisions where every single unit was chosen and verified to ensure strength, durability, and ultimately, safety.
If you're ready to level up, like and share this video. Subscribe and hit the bell to join the future of efficiency. ERA, your life optimized.